I'm Ollie. I just want to say thank you everyone for coming along and sort of giving me the opportunity to chat a little bit about some of the research I've been doing for the past year and a half now. So this is measuring humidity using refracted aircraft radio broadcasts, or as I like to call it, measuring humidity made plain and simple. Excuse the pun. All right. So just a little bit of context. The goal of my research is to basically improve weather forecasts across the UK. And there's two key ingredients to a weather forecast. Essentially, the first ingredient is we want some way to represent the atmosphere in a computer. So that'll be some weather model, like Alex spoke about, the UM that the Met Office uses. And this essentially contains all the physics describing how atmospheres evolve. So things like the Navier-Stokes flow equations, radiative transfer, all interesting stuff like that. And the idea is that when you have this model of the atmosphere, you can work out what some future state will be, so how that atmosphere will evolve with time. Now, that's just one ingredient in this recipe. The next key ingredient is good observations, because you might have heard the phrase garbage in, garbage out. And that applies to weather forecasts. And the idea is that if you put in observations that don't actually reflect what is happening in the atmosphere, your weather predictions aren't actually going to tell you anything useful, really. So my goal is to improve this last bit, this observations bit. So how do we actually combine observations with our weather model? I like to think of it as a balancing act. So what I mean by that is your future forecast, you want the best of both worlds. You want the new information, the observations, but you also want to ensure that it's meteorologically consistent. So it obeys the laws of physics, things like that. So let's say we've got some future forecast, and we bring in some observations. Now, in the first scenario, let's say these observations have massive errors. So we're not confident that they actually tell us what the true state of the atmosphere is at that time. We don't want our future forecast to be too heavily influenced by the observations. We don't want it to be swayed off into some unphysical outcome. So what we do is instead we weigh it more towards what we already know, so the background, the previous short-term forecast. Vice versa, if our observations have very low errors, we want our future forecast to reflect the true state of the atmosphere, which we get from those observations. So this is a dynamic thing. During the assimilation window, where we put observations into the weather forecast, you're continuously evaluating how good those observations are, along with how well we already know what the atmosphere is doing from the previous forecast. So I'm going to focus on the observations side. So Alex mentioned how the UK has 200 weather stations across the land. And these are a fantastic source of information. But a major problem with these is that they only tell you what's going on right at the surface. You're missing out all the information about what the humidity is doing above that. We also have weather balloons. So you attach something called a radiosonde to a weather balloon, and that ascends through the atmosphere and constructs a vertical profile of the humidity, pressure, and temperature. But these have major limitations. So this map here is basically where we launch weather balloons across the UK. And you can see that in between these weather stations, you're not getting any information at all about what the humidity is doing. And these are only launched at most twice a day. And humidity varies quite significantly over the course of 12 hours. Think of a thunderstorm. You know, it forms and it's gone within those 12 hours, and you're just completely missing out this information. So what we really need is a cheaper and more adequate way to measure humidity. So what we do is we say, okay, measuring humidity, it's really difficult, so let's just not bother. What we do instead is we find something called a proxy. So this variable depends on humidity, but is much easier to measure. And one such proxy is something called the refractive index. So you're probably more familiar with the refractive index in terms of something like water or glass. And it essentially tells you how much light slows down inside that medium. So take, for example, diamond with a refractive index of, let's say, 2.4. So what that means is light travels 2.4 times slower in a diamond than it does in a vacuum. And the air also has a refractive index, and it's given by this equation here, this one. So, oops. All right, so it's 1 plus some variables that depend on the air pressure, temperature, and humidity, this water vapor pressure, E. So if you know what the pressure and temperature is, which we already know pretty well from weather forecasts, and you know what the refractive index is, you can work out what this water vapor pressure is. So that equation previously is 1 plus this stuff here, which don't worry about too much. But we only care about that excess, that bit above 1. That's the only bit that the atmosphere contributes to the refractive index. So what we do is we say, okay, shave off the 1 and scale up that excess by about a million. And you get a number of around 350, which is much easier to work with and only depends on the atmospheric conditions. And this is something called refractivity, and it's the excess above unity of the refractive index. So looking here, this is a profile of how the refractivity changes with height. So 10 kilometers is about where the stratosphere starts and where aircraft fly. And you can see that most of the refractivity is actually below this line, so this sort of area under here. And then as you get up towards space, sort of above 40 kilometers or so, the refractivity drops down to 0. And there's basically no contribution of the atmosphere to the refractive index there. So I want to focus on one way we can measure this refractive index, mainly because it has its origins in astrophysics. So this is something called radio occultation. So this was originally used to profile the atmospheres of Venus, Mars, and most recently Pluto. And the idea is that you have some satellite, and this is broadcasting radio waves. And those radio waves, as this satellite passes behind the object of interest, those radio waves pass through the atmosphere. And as they do, they encounter variations in the refractive index, or the refractivity. And instead of following a straight path, they follow this curved path. And the amount this curves is a function of the refractive index at this point here. So if you can measure this bending angle as this signal moves down through the atmosphere, you can build a profile of the refractive index of the atmosphere. And from that, you can work out the pressure and temperature. So yeah, this was recently used on Pluto to sort of work out the pressure and temperature with altitude. And we've also done it for other things like the rings of Saturn. So it has a lot of links in astrophysics, and these days it's a really important source of refractivity information on Earth. With the invention of GPS satellites, we have thousands of satellites orbiting the Earth, and thousands of these events, these occultations events, occurring every day. It's a really important source of information. So let's talk a little bit about how the refractive index influences light. So you're probably pretty familiar with this equation, Snell's law, from high school. And it essentially tells you that the product of the refractive index with the sine of this angle with respect to the normal is constant along the ray path. And you get some really funky effects where essentially the light from inside the water hits this boundary between the water and the air and undergoes this bending, whereas the light traveling just through the air follows a straight line. So it shifts the apparent position of objects in material with different refractive indices. And this effect also occurs in the atmosphere. So the refractive index of the atmosphere is highest at the surface, where the atmosphere is most dense, and it decreases with height. And we essentially use a sort of modification of Snell's law. We just add in this radius term to the n cos or sine theta term. And this is conserved along the entire ray path. And what you find is that a ray passing from the denser low regions of the atmosphere to the higher regions of the atmosphere where it's less dense, it follows this curved path. And this is really interesting because what it does is it effectively increases the range you can see. So when you watch a sunrise or a sunset, the sun can actually be just below the horizon. But because its light is bent by the atmosphere and followed this curved path, it looks like it's higher in the sky. So when you first see that disk of the sunrise, you're actually seeing basically a projection of it because the true position of the sun is actually below the horizon. Here's another interesting example of refraction where this is from the International Space Station, and you can see the moon as it passes near the limb of the Earth. Different parts of the moon, the light from the different parts of the moon are refracted differently, and it becomes sort of squished and elongated, and you get some really bizarre effects. So these are some even more extreme effects from refraction. So this is something called Fata Morgana, and this is essentially where ships appear to float on the horizon. And a lot of people think this was fake, but this is actually a real image. This is from the Scottish Open in Aberdeen a few years ago. And just this ship here is actually below the horizon, but because the light's been bent over the curvature of the Earth, it's actually shifted And it's really bizarre. It's just floating up here. Really incredible stuff. You're probably more familiar with mirages. So this is the opposite effect, where basically the air near the surface is heated by the road, and it has a low refractive index. So instead of following this sort of curved arc, it sort of bends down and then back up. So what you're looking at here is basically this region of the sky, but the light's sort of being bent up from the ground. So yeah, some weird effects. And then this image, I'm not gonna lie, I have no idea what's going on here. It's some really strange refractive effects. You can kind of see how the mountain up here, the image looks fairly normal. And then this band here, you've got sort of inversions going on and sort of mirror images. And there's some bands here of air which is significantly denser, I think. And it's just sort of refracting the light in really bizarre ways. So it's really interesting stuff. So that was just a little bit of a background on atmospheric refraction and also observations. So how can we exploit refraction to actually get better weather forecasts? So the basic idea is that aircraft, they emit radio waves. And just like any other form of light, these are refracted by the atmospheric layers. And if you can measure this bending, so how much this light bends as it passes through the atmosphere, you can work out what the refractive index structure is. So how do we actually measure this bending? How do we measure the sort of shifting in the position of the aircraft signal? So we use a technique called interferometry, which is used extensively in astrophysics to image celestial bodies and astrophysical objects. So the basic idea is that if you have some source of light up here, some source of radiation, that radiation will hit this antenna and then has to travel some extra distance to hit this antenna. It's a bit like if you hear a sound to your right, you can kind of work out where that is because there's some delay between it hitting your right ear and your left ear. It's the same sort of principle. So using this technique, you can work out the direction where some radiation comes from. So you might have seen this image recently of the black hole in the center of the Milky Way. And this was imaged by basically combining the signals from interferometers at different locations on Earth to effectively have a massive baseline. And the resolution of this is just incredible. So this is equivalent to taking an image of a tennis ball on the moon from the surface of the Earth. So you can just imagine how tiny these angles are, just how precise this technique is. So how we apply this technique is essentially, rather than having antennas sort of separated horizontally, we have antennas separated vertically by some vertical baseline. So when these aircraft broadcast radio waves, those signals hit the first antenna at the top, and then they hit the bottom antenna. And the difference, there's a phase difference accumulated between the two. Now, what I mean by that is, imagine these radio signals as like ocean waves, and they have peaks and troughs, and they sort of propagate like that. So when we receive the signal at the top antenna, the wave will be at some high point. So it'll be at the top, for example. Now, the signal has to travel some extra distance to hit the bottom antenna. So it'll be at some other point in its wave cycle. So here it's at a trough. And there's a difference. This is what we mean by phase difference. So there's a difference in the point of the wave between the two antennas. Now, we can't actually measure this distance directly, but we can measure the phase difference. And from that, we can work out this distance d. And then it's just a case of simple trigonometry to work out this angle of arrival. So this is some real data. This is what the data actually looks like. So what you're looking at here is, along this x-axis, is the reported or unrefracted angle of arrival of the aircraft. So this is the angle that you would expect the radiation to, or the signal to arrive at, assuming no refraction occurred, if it just followed this straight line path from the aircraft. I don't know if I can see it. There we go. So that's along the x-axis. And then along the y-axis is where we actually do receive the signal at. So this is after it's undergone refraction, and this is the direction that we actually receive the signal at. And you can see that sort of higher elevations, these two angles are roughly the same. And what that's telling us is basically there's not much refraction occurring at sort of like 10 degrees altitude above the sky, above the horizon. And there's not much refraction occurring. These two lines are roughly the same. Now, as you get below around 3 degrees, they start to diverge. And the ray is following actually a more and more curved path. There's a deviation. And this is the bit we're interested in, this deviation, because this tells us about the refractive index structure and also the humidity. So during the day, this will vary. So when you've got periods of steeper refractive index gradients, so if it's very sort of dense at the surface and then decreases quite quickly with height, this will be much greater. and then if there's a lower gradient, this will be closer to this line of equality. So this tells us, this deviation tells us a lot about the atmospheric conditions at the time. So I mentioned how essentially the refractive index is a really small number. It's like 1.0003. It's a tiny little bit above 1. I mean, take water, for example, that's 1.3. It's orders of magnitude larger. And because the refractive index variation is so small, these angles that we have to measure are tiny. So this is about the size of the moon in the sky. It's about, at its maximum, about half a degree. So that's how much it spans in the sky. Venus at its maximum, at its closest approach, spans about 0.016 degrees. So we actually need to measure smaller than the diameter of Venus in the sky to get anything useful out of this data, to get meteorologically useful information. And you can think of Venus, it just looks like a star in the sky, a bright one albeit, but you can't resolve anything with the naked eye. So these are quite small angles. So I've been talking about angles a lot and sort of measuring the angle of arrival, but how do we actually get the refractive index structure from this? So I like to think of it as like tuning a radio. So we have, this is some atmosphere, for example, and we have the refractive index of the surface, and you've got different levels to the atmosphere, different layers of the atmosphere, and they each have a different refractive index because they have different temperature, pressure, etc. And you basically want to tune these, so change these refractive index levels so that the refraction you see in reality in the observations is what you see in the model. So you basically want to model this path so it matches what actually happens in reality. And you can kind of see, this is some results I got a while ago. And basically, you can kind of see the model tuning each of these values. So I'm using relative humidity here. And that's only because I'm sort of tuning the refractive index by changing the humidity. I'm fixing the pressure and temperature. And by changing the amount of water vapor, I can change the refractive index. So they're essentially equivalent. But you can kind of see it tuning and then sort of falling on this true solution. So this is the correct solution, this black line. You can kind of see over time it starts to fall on this correct line. And this is an optimization problem. So this comes up in a huge range of fields, especially in physics and engineering. So you essentially want to minimize this function j here, describing the difference between your model and your observation. And you want that to be as small as possible. And one of the most recent examples of this is like in machine learning. So for example, when you're training a neural network, you want to minimize the difference between the model's predictions and the training set. So you want it to be as accurate as possible. So here's some more data that we've got, which just shows the range we can get from this technique. I mean, it's just honestly exceeded our expectations quite substantially. But what you're looking at here is a map of, this is France, and then we're around here, so Exeter is around here. This was from an interferometer installed on the physics tower, looking out towards the interior of France. And each of these lines are a flight path, so they're actually composed of individual aircraft broadcasts. And you can see that we can see aircraft right in the interior of France. So this is well below the horizon. Like, without refraction, you would not be able to see these. But because of the way the atmosphere works, the light from these signals is bent over the curvature of the Earth towards our receiver. So we have 500-kilometer range from a single receiver, and also this spread in data as well. I mean, it's just honestly fantastic what a single interferometer receiver can do. So you can imagine a network of these across the UK. You could almost cover the entire UK. So I've been kind of tooting my own horn a little bit, talking about the benefits of this method, in terms of, I should also mention it's a lot cheaper than some existing technologies. But yeah, I've been tooting my own horn a little bit, talking about how the method is cheap. We've got good sampling of the data, etc. But we are facing some problems. And one of those problems is that we only really care about the direct signal from the aircraft. So this is the signal that's undergone refraction, and it's the one we want to measure. But the problem is we've got all this stuff in the foreground, which is quite reflective. So radio waves bounce off these buildings and are received by the antenna, and they contaminate this direct signal. So it completely scrambles the data. So ideally, we want to just block out these signals from interfering with the direct signal. One idea we had was kind of brute force it. Go into the workshop with a hammer and whatever, and just build a screen to just block the signals. So you can imagine you'd have the antenna sort of here, and this would just block these reflected signals from reaching the antenna. We're going to be trying this in April Fingers crossed it works, but yeah, experiments often don't go to plan, but that's the nature of science. It's just one of those things. So I want to talk a little bit about one other method we looked at. So this is what my supervisor came up with. So what you're looking at here is flight paths. So each of these points is an individual aircraft broadcast. And you can kind of see the flight paths as the aircraft move through the sky. But we've got these weird wave-like structures. It's really bumpy. Aircraft don't, well, you'd hope they wouldn't sort of just jump up and down and up and down. I don't think the passengers would be too happy about that. But we have these weird wave-like structures, and that's because of those reflected signals interfering with the direct signal. So my supervisor had the idea of, okay, the direct signal is actually the shortest time signal. So this is the most direct route light can take. And this is from Fermat's principle and Snell's law. So it's the shortest time route. So these reflected signals will actually be received at some later time. So why don't we just take the phase measurements from the leading edge of the signal, so the very first signal we receive, and then just cut it off before we can receive the reflected signals. So after we did that, after we took the phase measurements from the leading edge of the signal, this is what we saw. Those wave-like structures are just almost completely eliminated. And the variation of these signals is approaching that 0.01 degree accuracy that we need. So we're making some exciting progress in terms of minimizing errors and hopefully getting towards better meteorological data. So to sort of wrap it all up as a summary, we need better weather forecasts. I'm sure, as many of you know, weather forecasts in the UK are sometimes a bit rubbish. That's a bit harsh, but oh well. We've also found a new source, we've potentially found a new source of humidity observations to improve those weather forecasts. And if fully realized, this method could be superior to existing methods in terms of the density of the humidity measurements we can make, and also the temporal resolution, and also the cost. But there's a lot of work to get it up and running, and that's what I'm working on at the moment. So that's been my talk. Thanks once again, everyone, for coming along and giving me the opportunity to talk about this. Thanks.